Hello again, Physics 20 Advanced Placement students. In today's lesson, we are going to talk about torque in terms of how a force can generate torque on a rotating rigid body. Then also talk about torque equilibrium, which will involve uh, identifying how we can account for torque generated by different forces and what we can do to make sure that a rigid body will not actually undergo rotation. I'm going to start off just with a quick set of discussion questions. I'm going to read them off to you. I'm not going to give you the answer to these questions. I just want you to think about this. And after we go through this lesson, you can then come back to it and then use your understanding of torque to try to correctly respond to them. I'm not going to come back to them though, just for you to kind of food for thought for you. All right, so what we'd have is in the diagram shown below, all forces acting on the door are equal in magnitude. So this would be a top view perspective of a door. And it says for each diagram, rank the forces in terms of their effectiveness to rotate the door open about the door hinge, and then identify what's the defining factor that's contributing to whether the force is effective at opening the door or not. So there's actually two cases that you can see in this illustration. So in figure 1, you have two forces. You have F1 and you have F2. They're both the same force magnitude. What's different, though, is the distance from the fulcrum. So this is like your door hinge to the forces. So F2, there's only a short distance from the door hinge to the force. F1, there's a large distance from the door hinge to that force. So which of those forces would be more effective at opening the door? Again, I'll leave that for you to think about. In figure 2, all of them, all forces, F1, F3, and F4, they're all located the same distance from the door hinge. What's different here is the angle of the force with respect to the door. So F1 is making a perpendicular angle relative to the door. F4 is parallel to the door. And then this force would have a small angle compared to the door, which we could call theta. So how would you rank those ones in terms of most effective to least effective in opening the door? Okay, so you can think about that. We're going to focus on talking about torque. So torque, which is represented by the Greek letter tau, it's kind of like a handwritten T symbol, just the vector on top of it. Okay, so if you have a door and you apply a force, F, in this fashion, you will generate torque about the door hinge. What exactly is torque? Torque is essentially a force that causes an object to rotate. Okay, that's how we define it qualitatively. If you exert a force on an object and that force can make the object rotate about some kind of axis of rotation, so the axis of rotation is kind of like just the pivot point in which everything else is rotating about. So that would be the door hinge. So your door hinge would be your axis of rotation, because all parts of the rigid body are rotating about it. And if that force can cause the door to rotate, we refer to that as generating torque. So it's a force that can cause rotation. To calculate torque, torque is equal to the vector cross product. Okay, I'll talk a little bit more about a vector cross product on the next slide, but not too much right now. We'll leave that for the advanced placement 30 material. So you have torque is equal to R crossed with F. F just represents the force that the rigid body is being subjected to. Okay, so what's R? R is a vector, you can see in the diagram, that starts at the axis of rotation. So its starting point is at O, and it points to the location where your force is acting. So my vector would start at O and point to the doorknob, which is where the force is actually acting in this picture. R is a position vector. And it's a position vector that points from the axis of rotation to the location where F is going to act on your object. If you take the magnitude of R is what we refer to as a lever arm. So your torque is equal to the cross product of this position vector from the axis of rotation to your force multiplied by the force itself. Let's break this into two parts though. So torque is a vector. Let's look at both its direction and its magnitude separately, starting with the direction. I've changed the force just a little bit. So in this situation, the force is actually perpendicular to the doorknob. To determine the direction of torque, we can also use the right-hand rule. Now, here's how this would work. Okay, to identify the direction of torque, what you should ask yourself is, from this perspective, if you pulled on this doorknob, okay, towards the top of the page, what rotational direction would it cause the door to rotate? Would it cause it to rotate clockwise, or would it cause it to rotate counterclockwise? Well, from this perspective, if you pulled on the doorknob towards the top of the page, that would cause the door to rotate in a direction that would be like this. That direction is counterclockwise. So that's how we identify the direction of torque. Just look at a force and ask yourself, if this was the only force acting on my object, what direction would it cause my object to rotate about the axis of rotation? Clockwise or counterclockwise? So in this case, that force generates counterclockwise torque. And according to the right-hand rule, counterclockwise torque is going to be positive torque. The right-hand rule, again, is like you take your thumb and you point it out of the page at you, look at the curl of your fingers, and the curl of your fingers tells you the direction of the positive rotational direction, which would be counterclockwise. Okay, so that's my direction. How about the magnitude? The magnitude of torque can be calculated by, it turns out if you figure out the magnitude of any vector cross product, it turns into the magnitude of torque is the magnitude of your position vector times the magnitude of the force multiplied by sine of theta. Or we can just drop all the magnitude of the vectors and just write down tau is equal to RF sine theta. So that'd be my equation, just exclusively dealing with the magnitude of the torque. The direction we can figure out just logically by asking yourself, what direction will the force cause the object to rotate? In this equation, theta represents the angle between your position vector and between the force. So in this diagram at the very top, let's use red. So your position vector goes from the axis of rotation to the location of your force. So that would be R. In this situation, the angle between the force and between that R vector would be theta is 90 degrees. Well, what happens if we go back to that illustration where we had the force at a little bit of an angle? Well, this interior angle here would represent theta. So that's the angle between your force and between the position vector. So you can kind of get a sense now of like, okay, how do I maximize torque? Well, there's two ways to maximize torque. One, you need a bigger lever arm. If you have a tiny lever arm, then it's really, really hard to generate torque about an object. And two is, a bigger force will generate bigger torque. But the other thing is you want to try to make your force and your lever arm perpendicular to each other as possible. The biggest value that sine of theta can be is 1. When is sine of theta 1? When it's 90 degrees. Okay, so we want to try to make these two things perpendicular. So that's how we'll maximize our torque. I suppose 3 things to maximize it. Big lever arm, larger force, and try to keep the lever arm and the force so they're perpendicular to each other. Now we can actually take the force, we can break it into 2 components. We can break it into a horizontal or parallel component, or we can break it into a vertical or a perpendicular component from our perspective. If you want to calculate the perpendicular component of the force, it would just be F times sine theta. So what this tells me is F sine theta So why F sine theta in the equation up here? The F sine theta is just forcing you to take the perpendicular component of the force relative to the lever arm. So we could, if we wanted to abbreviate the torque equation, we could represent it as torque is equal to the magnitude of your lever arm multiplied by whichever component of the force is perpendicular to the lever arm. Generally, this is the equation I like to start with when I solve problems, okay? R is F perpendicular, because depending on the angle, it might not always be sine of theta, okay? So just do whatever you can to take the perpendicular component of the force. Okay, we'll see more about this in the second example in a moment. So yeah, the note is only the perpendicular component of F relative to the lever arm will generate torque. This parallel component here does absolutely nothing. Okay, so if you actually add a force that's parallel to the lever arm, it will not generate any torque. Back in the dynamics unit, we talked about static equilibrium. So static equilibrium was a situation where all of our forces were balanced and an object did not move. With the introduction of torque, we also have to worry about torque equilibrium. So torque equilibrium means if I have a bunch of forces acting on an object, can they all offset so they don't generate any torque at the end of the day? So consider this situation. So in this scenario, it's kind of like a weird looking, you could pretend it's like a weird looking teeter-totter. I realize that most teeter-totters would actually have the fulcrum directly in the center as opposed to shifted towards the left-hand side. So what we have is we have our axis of rotation, the fulcrum, point O, F1x on the left end of the board down, F2x on the right end of the board down. And we have R1, which is the lever arm from the axis of rotation to F1, and R2 is the lever arm from the axis of rotation to F2. Now, each of these forces generates torque. So pretend for a moment that F1 does not exist, and the only force acting on this teeter-totter was F2. Well, what direction would that generate torque? If F2 is the only force acting on this, it would cause the teeter-totter to rotate in a direction like this. So we'd say it generates torque, tau 2, and from our perspective, that would be clockwise torque. Okay, now let's pretend that F2 doesn't exist. And then let's look at what would happen with F1. If F2 didn't exist and F1 was the only force acting on the teeter-totter, what direction would that cause the teeter-totter to rotate? Well, if you took the teeter-totter and pushed down at this end, it would then cause it to rotate in a direction that would be like this. So we could call this tau 1. Now, tau 1 is causing the teeter-totter to rotate in a counterclockwise direction. So what I have here is I have two offsetting torques. F2 wants to cause the teeter-totter to rotate clockwise. F1 wants the teeter-totter to rotate counterclockwise. Torque equilibrium would involve the sum of these two torques being equal to 0, where they do offset. So a rigid body, when you're in torque equilibrium, a rigid body will not rotate about a fulcrum O when the sum of the torques about O is equal to 0. Okay? We can represent this in an equation that looks like sigma tau, and then we have the O here just indicating about the center of rotation is equal to 0. So in this situation, presumably they're going to add up to 0 because counterclockwise torque is going to be a positive number, and then clockwise torque is going to be a negative number. So if the two torques generate the same magnitude and I add a positive and a negative, well, those opposite numbers would just cancel each other off. However, you also need to worry about, if we're looking at torque equilibrium, yes, the sum of the torques need to be equal to 0. In addition to that, we also need to make sure our other equations of motion are equal to 0 as well, which means the sum of the forces in the x is equal to 0, and the sum of the forces in the y would also be equal to 0. If all three of those conditions are met, we are truly in torque equilibrium. So going back to the dynamics unit, we didn't really account for torque, but not a huge deal back then because we were only treating our objects like particles where you couldn't really generate any torque anyways because they don't have any size. Well, now we have size and now we have to worry about this. Okay, so quick question. Which force must be larger in magnitude in order for the beam to not rotate about point O? Okay, well, let's look at the torque equation. So if we did this, so let's say the sum of the torque about point O is equal to 0. Now, we need to establish what direction we want to be positive. So positive would be the direction according to the right-hand rule. So I just draw a little tiny arrow that points in a counterclockwise direction. Now, to expand this torque equation of motion, what this means is any torque that causes rotation clockwise, you write as positive, and if it generates counterclockwise positive and clockwise be negative. So which of these torques actually generates positive torque? Well, it'll be tau 1. So we'd write down positive tau 1 because that is counterclockwise torque. If it generates torque in the opposite direction, the clockwise direction now would be negative. And that's what tau 2 does. So tau 2 generates clockwise torque. Okay, so that's equal to 0. Now, we can expand this a step further because what we know for torque, and this is usually where I jump to in terms of writing down a torque equation, your magnitude of torque is equal to your lever arm times the perpendicular component of your force to the lever arm. Okay, so tau 1 would just be, it would be R1 times F1. Okay, F1 is a perpendicular force already to the lever arm. Tau 2 would just be R2 times F2 is equal to 0. Okay, so it says which force must be larger in magnitude so we can actually truly have torque equilibrium? We'll look at it here. If R1 is small,
Howard, can you call me?
If R1 is small and R2 is big, what would the force values have to be in order to kind of offset each other? Well, if I want to generate the same torque, if R1 is small, that means I need F1 to be big. And if R2 is big, I would need F2 to be small to generate the same amount of torque. So in this case, I would need F1 to be bigger than F2 in order for this to be in torque equilibrium. Okay, let's look at some examples now. Okay, so in an isometric exercise, a person places a hand on a scale and pushes vertically downward, keeping the forearm horizontal. This is possible because the triceps muscles applies an upward force M perpendicular to the arm, as the drawing indicates. The forearm weighs 22.0 newtons and has a center of gravity as indicated. The scale registers 111 newtons. I want to determine the magnitude of M. Okay, the first thing I'm going to do is I'm going to draw a free body diagram of the person's forearm. Okay, so I'll do FBD of their forearm. Okay, so I'm going to represent their forearm just with a really large rectangle. Okay, the elbow joint, this would be the fulcrum. So we'll call that O, and I'll just label it on the diagram. I like to try to represent any situation just with like a teeter-totter type diagram. Okay, so we're going to call that point O, and point O is the elbow joint. Okay, so what do we have acting on this forearm? Well, on the very left end of the forearm, there's this force M, which is the triceps muscle applying an upward force. So we're going to call this force M. On the right-hand side, the person's pushing down on the scale. Now, when you push down the scale is going to oppose with an equal and opposite force. So we're going to call that Fn. Fn is the normal force from the scale pushing back against me. Now we're still missing a couple of other forces. Okay, now this forearm, it has its own mass and it has its own weight. Therefore, we need to account for the force of gravity acting on it. Well, where do we draw the force of gravity on a rigid body? At the center of mass. So the center of mass of this guy, we're assuming it's a uniform density. The bone would just be, actually, I don't think it is uniform. It shows me here that it's located at this position. So it's at this position here. So the center of gravity is located somewhere about, I'll just sketch it in here. Yeah, sorry, it's not directly at the center of this forearm, but it does show me in the picture where it's located. Okay, so that's CG, and then we could draw a force down, which we're going to call FG. There's one other force acting on the forearm, and it would be the force that the elbow joint exerts on the forearm. Now, I don't know what direction it is. It could be up, it could be down. I don't really know, so I'm just gonna have to go ahead and just make a guess, okay? But you're actually gonna see it's not gonna make a big deal here. So we're gonna call this, I'll say FE for the elbow. Now I'm gonna label a few other things. I'm also going to label all the different lever arms just to make that clear in this picture. So let's do that with a different color. So I'll do black for the lever arms. So lever arm is always measured from the axis of rotation to where your force is located. So we'll call this one, the distance from O to the triceps muscle force, we're going to call RM. We're going to call this from the elbow joint to the center of gravity, we'll call that RG. And then we'll do one more. We'll go from this one to the normal force, and we're going to call that RN. Okay. What about RE? What's the lever arm for the elbow force? There is no lever arm because the elbow joint force is already at the fulcrum position, which means that FE is actually not going to generate any torque at all. So FE really doesn't even need to be mentioned in terms of discussing torque. Okay, this forearm is in equilibrium. Okay, we're pushing down the scale. We're not actually moving our arm. Okay, and we want to figure out what the magnitude of M is. Now, you might just be like, okay, wait a second. I can just go ahead and use like a simple equation of motion and do it. Because what I can do is I can just go sum of the forces in the Y is equal to 0. And then if up is positive, my equation of motion would be M plus FE minus FG plus Fn is equal to 0. Now, that equation of motion is correct, okay? Except we don't really know what the direction of Fe is, but that equation of motion is right. M points up, it's positive. Fe potentially points up, it's positive. Fg points down, it's negative. Fn points up, it's positive. The problem is we can't calculate M here because I don't know what Fe is. So if I went straight to the vertical equation of motion, I'd be stuck because I have one equation and I only have two unknowns. So in order to solve this, I'm going to have to use a torque equation to deal with it. Okay, so here's how we do it. Okay, so let's write down our torque equation of motion, which tells me that assuming any torques that point counterclockwise are positive, I'm going to find the sum of the torque about point O, which is the elbow joint, and that's going to be equal to 0 if I'm in torque equilibrium. Okay, now I need to start identifying which forces are going to generate what kind of torque. So let's go back. Okay, let's start off with M. If M was the only force that was acting on this, this forearm above the elbow joint, what direction would M generate torque? Well, think about it. If this is a teeter-totter and you pulled on the left end, that should cause the teeter-totter to rotate in a clockwise direction. So a clockwise direction would actually be negative torque. So we're going to say negative tau M. So the force M generates negative torque in the clockwise direction. How about the elbow force? The elbow force does nothing. Okay. The elbow force does not have a lever arm at all. Therefore, it doesn't generate any torque, so we don't have to worry about it. This is actually a very clever way of hiding a force that you don't want to deal with. Because if you sum torque about that point, and it would have no lever arm at that point, and therefore it can be ignored. So we don't need to write Fe in the torque equation because it generates no torque due to having no lever arm. So we're kind of hiding it in a way. Okay, how about Fg? If Fg is the only force acting on this teeter-totter, what direction would cause a teeter-totter to rotate? Well, if I pull down here, it should also cause the teeter-totter to rotate in a clockwise direction. So I'm going to turn this into negative tau g. Again, this is because you're generating clockwise torque. This is because you're generating clockwise torque. Okay, so right now it seems like how can you get torque equilibrium is not going to be possible because we have two clockwise torques. We need a counterclockwise one to offset it. Well, that's what the normal force on the scale is going to do. Okay, so if you only applied Fn on the scale at the very right end, this would cause the teeter-totter to rotate in a direction that would then be counterclockwise. So that's going to be plus tau n. We'll use n for the normal force. Okay, so that's my torque equation of motion, and we're going to expand it a little bit further. Okay, so in terms of magnitude of torque, let's ignore that vertical line. Okay, magnitude of torque is equal to the moment arm times the perpendicular component of the force to the lever arm. Okay, so let's start to break this down. So tau m would be the lever arm Rm times the perpendicular component of the force m to the forearm. Well, it's already perpendicular, so we can just write it down as negative Rm times the force m. Tau g would just be the lever arm Rg multiplied by the perpendicular component of the force of gravity to the forearm. Well, it's already perpendicular, so it would just be Fg. Plus the lever arm for the normal force multiplied by the perpendicular component of the normal force to the forearm. It's already perpendicular, so it's Fn. Okay, we need to solve for m here. Okay, so I'm going to do this all in one shot. So what I'm going to do is I'm going to bring the negative Rm m term over to the right-hand side. And then I'm just going to divide both sides of the equation by the lever arm. So that would turn into m would then be equal to Rn Fn minus Rg Fg. And then we're going to divide this all by the lever arm Rm. Okay, now we can plug numbers in. Okay, so what is the distance from the elbow joint to the normal force? Well, look at the diagram here. It's 0.300 meters. What normal force is the scale pushing back on the hand with? I believe that force is 111 newtons. Subtract. Rg is the lever arm, which is from the elbow joint to the center of gravity. So that's 0.150 meters. Multiplied by the force of gravity. I believe the problem tells us that the forearm weighs 22.0 newtons. And then we're going to divide by Rm, which is the lever arm from the elbow joint to the location that triceps muscle force is acting. So that's that small distance, 0.0250 meters. Okay, and if we plug these numbers in, the top of its own set of brackets, and then we should get a number that is 1.20 times 10 to the third newtons. Okay, so we had to make use of our understanding of torque and torque equilibrium to calculate this force. Now, what if I said, and I'm not going to do it, but what if I said, okay, now calculate the elbow force? So what's Fe equal to? How would you do that now? Well, now you could use your equation of motion. If you go back to your equation of motion, sigma Fy equals 0, well, you now know what M is, you know what Fg is, you know what Fn is, so now you could go ahead and you could calculate the elbow force. I should just point out, if you did calculate it, if you get a positive number, it means that you guessed the direction correctly, okay? So that would mean that the elbow force is going to be straight up, okay? If you get a negative number, it doesn't mean that the magnitude is incorrect. It just means that you guessed the wrong direction on the free body diagram. So it would just mean that the direction of the elbow force would then be reversed. So it's just an interesting way of combining a couple of equations of motion. And the next example, which is a much more complicated one, I'm going to show you you can use a bunch of equations of motion. Okay, this one's tough. Also like one of my favorite physics problems. Okay, so you have a uniform board is leaning against a smooth vertical wall. Okay, so let's draw a picture. So I've got a wall. And there's a floor. Okay, this wall, it tells me it's smooth. Now this is important because this means that there's no friction. And then it's on the ground. And there's a board that's like, I'll just sketch the board in a different color. There's a board that's leaning against the wall. Okay, something like that. It tells me the coefficient of friction between the ground and the lower end of the board. So the ground does have friction. Okay, so ground has friction, has FF. Okay, and it says, find the smallest value for the angle theta such that the lower end of the board does not slide along the ground. So what it's asking for is like, what's the last point where you can have an angle theta before this thing starts to slide, okay? So we're maximizing our static friction, okay? So we want to get theta as small as possible, and we want to try to see like just how far we can push static friction in terms of its maximum. Okay, because if you exceed static friction, then it's going to start to slide. Okay, now this one's a bit tougher. Okay, so we're going to draw a free body diagram. This free body diagram is going to be very, very complicated. Okay, now before I do that, I just want to illustrate something about the board. So let's just draw the board. So here's my board. Okay, let's say the length of the board, I'm just going to call it L. So we'll call that L. Now it does say it's a uniform board. So uniform board means that its density is constant, which means that the center of gravity, CG, is going to be located right there, which means that the distance from one end to the center of gravity is L over 2. And same thing, the distance from the center of gravity to the right end is also going to be L over 2. Okay, so let's draw the board now. A big free body diagram. Now I'm going to heavily exaggerate the angle. It's a similar idea for like how I exaggerated angles in inclined planes because it's going to make specific angles very clear. So I'm going to make the angle between the ground and the board really small. So I'm going to do something along the lines of, let's do this. So I'm just really going to make that angle tiny. Okay, here's my board. Sorry, this is not a great picture of a board. Okay, so that is my board. Okay, so let's draw a few let's draw a few things here. So let's draw the center of gravity first. The center of gravity is located at the exact center. So that's going to be right here. Okay, that's CG, the center of gravity. And now we can start to draw some of the forces. Okay, so you would have a force that points straight down. We're going to call that force FG. On the left end of the board, you would have, there's no friction, but there is a normal force. So there'd be a normal force. And again, a normal force is always perpendicular to your surface and towards your object. So perpendicular to the surface would be perpendicular to the wall, and it needs to point towards the board, okay? So this is gonna be my normal force, and I'm gonna call that, let's call this wall 1, and we'll call the ground 2. So we're gonna label this as being, we're gonna say this is F and 1. Now on the right end, you have a normal force. Again, now this time around, it's perpendicular to the ground and towards the object, so that's going to point straight up. So that's going to be a normal force vector that looks like this. And we're going to label that as Fn2. And you also have some friction. Okay, so the board wants to slide towards the right. Therefore, the static friction force is going to oppose that motion and point towards the left. So your frictional force would point towards the left, and we'll call that F2. Okay, now that would be a complete free body diagram. We've got a big problem with our forces. What kind of forces or what part of my forces actually generate torque? Only the perpendicular components. So it's just the perpendicular components of the forces that relative to the board that I want to look at. So I'm going to take every one of these forces, I'm going to break them into both a perpendicular component and into a vertical component. Sorry, perpendicular component and a parallel component. Okay, so let's start off with the normal force 1. So the parallel component would be in the same direction that the board is. So it would look like this. And your perpendicular component would point towards the board. Okay, so we're going to call this one Fn1. And we'll call that Fn1 parallel, because it's parallel to the board. And we'll call this one Fn1 perpendicular. How about the force of gravity? Let's draw the perpendicular component first. So the perpendicular component relative to the board would look like that. And then its parallel component relative to the board would look like this. We're going to call this one FG perpendicular. And we're going to call this one FG parallel. How about normal force 2? Okay, so we'd have a parallel component that points in this direction, up and towards the left, and a perpendicular component that would point in this direction. So we're going to call this one Fn2 perpendicular, and we're going to call this one Fn2 parallel. Not that we care about the parallel components, but I'm just going to label it just for the sake of completion. So parallel. And then we have one more force, which is the frictional force. So the frictional force, we can draw a parallel component that goes up and towards the left, like this. So we're going to call that one FF2 parallel. And then we'll draw the perpendicular component that points towards the board. And we're going to call that one FF2 perpendicular. Okay, now the reason that I heavily exaggerated the angle of the board is because it's going to make it obvious which angle fits into my components diagrams. Okay, so let's say this is the angle relative to the ground, theta. Okay, theta, I tried to make it a small angle, okay, because hopefully that's going to make it easy to see where theta goes in all these components diagrams. Okay, so let's look at the first one here. Where's theta going to be? Is it going to be this angle that's the left one here, or the one that's going to be on the right side? This angle to me looks smaller. Okay, so I'm going to label this one as being theta. How about the gravity one? Is this going to be the small angle, the top one, or is this going to be the small angle, the bottom one? The top one looks like it's a smaller angle. Okay. And if I exaggerate the angle, I can just use the exaggeration of the angle to get the angle correctly in the components. Otherwise, you got like annoying mathematical work to prove which is which. Okay, how about this one? What's a smaller angle? Is it going to be this top one here or this bottom one? I'm pretty sure it's the top one that looks like it's a smaller angle. And the final one, which is a smaller angle? Is it this right one here or this one on the inside? I think it's going to be the right one here. Okay, so finally, we've got a free body diagram. We showed all the components and we have the angles theta in it. Now we're ready to finally start to attempt to solve this problem. This problem doesn't give you much information. The only thing it tells you is what the coefficient of static friction is between the board and the ground. So we're gonna write down our equations of motion, expand them, combine them, and just hope that a bunch of stuff is going to cancel off. And you're going to see it does, which is why I really, really like this question. Okay, now it turns out we're gonna have to do every possible equation of motion. We're going to do it in the x direction, we're going to do it in the y direction, and we're going to do a torque equation as well. Okay, so let's start off let's do the y direction. Okay, so sum of the forces in the vertical direction is equal to 0, which tells me my forces are balanced. Okay, so let's go back to the free body diagram now. Okay, which forces on this diagram point in the vertical direction? Well, there's two of them. Fn2 points up, Fg points down. So we're going to write the Fn2 as a positive force, Fg is a negative one. So this would expand to Fn2 minus, get rid of that horizontal line, Fn2 minus Fg is equal to 0. Those are my only two vertical forces. Fn2 points up, Fg points down. Okay, we can expand this. So this can turn into Fn2. Actually, I don't think we're going to expand. Let's leave it as Fg. So I'm going to say Fn2, bring this over to the other side, and this will just be equal to Fg. Now, I'm just going to box this equation right now. There's not really anything I can do with it. I don't know what the value of Fg is because I don't know the mass of the board. So I'm just going to box this and I'm going to call it equation number 1. Okay, now let's go to the x equation of motion. So the x equation of motion will be, let's assume right is positive. I'm going to find the sum of the forces in the x direction, and that is also equal to 0 if we're talking about being in static equilibrium. And again, we're at the instant just before that board is about to slide. Okay, let's go back to the FBD. So what forces point left or right? Fn1 points right, so it's positive. And you have one other force that points towards, Fn1 points right, it's positive. And you got Ff2, which points left, it's negative. Those are the only two horizontal forces. So this would then turn into Fn1 minus Ff2 is equal to 0. Now I'm going to expand. So Fn1 would be, subtract, what's the coefficient of static friction at the max point? So again, that's why it says the smallest angle. The smallest angle is going to be the instant just before static friction is overcome. So we're allowed to actually plug in the equation, mu(s) times, and we'll say Fn2, so mu times Fn. Okay, you're only allowed to use the equation Ff equals mu times Fn for static friction if we're looking at the maximum static friction point, okay, which is where the angle will be the smallest. We're just about to overcome static friction. Okay, I'm going to take this equation and I'm going to plug it in to this one. So I'm going to take this equation and just throw it in for Fn2. So if I do that, I would then have Fn1 minus mu s times, well, what's Fn2 equal to? It's equal to Fg is equal to 0. And we'll just solve for Fn1. So Fn1 would just be equal to mu s times Fg. I'm going to box that equation, and I'm going to call that equation number 2. Okay, so what's left now? The torque equation. Okay, so this is going to be the most complicated of the three. Okay, so first of all, right-hand rule, what direction's positive? Counterclockwise. So we're going to find the sum of the torque about point O is equal to 0. Okay, now the question is, what's point O? Now here's where we need to be clever, okay? We can choose point O to be either the point of contact on the wall, 1, or it can be the point of contact on the floor, 2. Now, if you can do either or. It doesn't make a difference which one you do, except one of them is a lot more clever. What you want to do when you're actually like picking a pivot point for a torque equation is pick a point on the rigid body that's going to hide more of the forces you don't want to deal with. So if I sum the torque about the left end, that would just hide Fn1 because then Fn1 wouldn't have any lever arm. So we could ignore Fn1. If you go to the right end of the board and you sum the torque about this point, both Ff2 and Fn2 generate no torque because they have no lever arm. Well, I want to hide more forces. Okay, I want my equation to be more simple. So I'm actually going to sum torque about, maybe we should just label this. So we'll say this is side 1. This is side 2. We're going to sum torque about side 2. Okay, this will be more clear as I actually expand the equation in motion. So let's say instead of saying sigma T0, we're going to say sigma T2. Okay, so that's the right end. Okay, now let's expand. Okay, so now we have to look back at our free body diagram and figure out which forces are generating torque. Okay, so the only forces, because what does Fn1 do? Well, we only want to look at the perpendicular component of the force. So what if your fulcrum is at this end? Okay, so here's my fulcrum of the teeter-totter. If Fn1 is the only force that acts on the teeter-totter, what direction would it cause the board to rotate? Well, if it's fixed at the right end and I push up and towards the right with this perpendicular force, it should generate torque in a clockwise direction. Okay, so I'm going to call this negative tau due to Fn1 perpendicular. Okay, it's only the perpendicular component of Fn1 that actually generates any torque. Okay, and that's going to generate torque in a clockwise direction. Okay, let's go back. Well, how about the perpendicular component again? So always perpendicular component generates torque. How about the perpendicular component of the force of gravity? So if we're fixed at the right end and the only force acting on this is the perpendicular component of my weight, what direction would it cause the board to rotate? It should cause it to rotate in a direction that is counterclockwise. So counterclockwise is going to be positive torque. So we're going to say positive, the torque due to Fg perpendicular. Okay, so that's counterclockwise torque. What about the other two? How much torque does Ff2 perpendicular and Fn2 perpendicular generate about the right end? Nothing, because there's no lever arm. There's no distance from the pivot point I've chosen, so this could be point O, to these two forces. And that's why I chose to do the right end, because it's hiding two forces. So I don't have to worry about FF2 perpendicular or FN2 perpendicular, because from this right end of the board, no lever arm means no torque. Okay. You could, by the way, do it for the left end. It's just you're going to have more terms you have to worry about in your torque equation. Okay. So it's just a clever way of hiding things. If you want to hide forces, then sum the torque about the location of where those forces are located. All right, so let's expand now. Okay, this is equal to 0. Okay, so this would be equal to, well, let's label these now. So we're going to call this Rn1. So that's going to be the lever arm from the pivot point to the location of the normal force 1 times Fn1 perpendicular plus negative here. Okay, we'll call it the lever arm from the pivot point to the location of the force of gravity. We'll call that Rg. We're going to multiply that by Fg perpendicular, and that's going to be equal to 0. Okay, let's expand this a little bit. So what is the lever arm from the pivot point to normal force 1? Let's look at the picture. From the pivot point, the right end, all the way to where the normal force 1 is located, that's the full length of the board. So that's going to be L. The lever arm from the pivot point to the center of gravity is just half the length of the board, so that's going to be L over 2. Okay, so let's expand this. So this is going to turn into negative L, and then we have Fn1 perpendicular plus L over 2 times Fg perpendicular is equal to 0. Okay, now we also need to expand these perpendicular components in terms of the angle and the hypotenuse of the triangle. Okay, so let's look at Fn1 perpendicular. What is Fn1 perpendicular equal to in terms of theta and Fn1? Well, it's side opposite. So sine of theta would be the magnitude Fn1 perpendicular over Fn1. Therefore, I can expand this to negative L multiplied by Fn1 times sine theta plus L over 2. Okay, let's go back now to look at what Fg perpendicular is. Okay, Fg perpendicular, how does that relate to this angle theta? Well, it's the adjacent side. So cos of theta would be Fg perpendicular over Fg. So we're going to use cos. Okay, so this would then be Fg times cos of theta. By the way, this is why I like to write down torque. It's just equal to R times F perpendicular, as opposed to writing it as RF sine theta. It might not be sine theta. Okay, it really depends on what the actual angle is when you've constructed your diagrams and how you've labeled the angle. So I just start off with torque as R times F perpendicular, and then do whatever geometry or math you need to do to figure out how the perpendicular component expands. Okay, that is going to be equal to 0. Now I'm going to do one substitution here. So now I'm going to take this equation and I'm going to throw it in for Fn1. So when I do that, this would then turn into negative L times mu s g. Oh, sorry, mu s fg. Whoops. Negative L times mu s fg times sine theta plus L over 2 times Fg cosine of theta is equal to 0. Okay, I'm going to add this negative term to the other side. So I'm then going to have L over 2 Fg cos theta is equal to L mu s Fg sine theta. Now here's where we're going to have a payoff in keeping everything in terms of variables, which we had to do. What cancels? Common L on both sides and common Fg on both sides of the equation. So now I'm going to be left with cosine of theta over 2 is equal to mu s times sine theta. Okay, let's get mu s isolated. So to get mu s isolated, we're going to, oh no, what do we want? We want the angle. Okay, let's collect the angles on both sides of the equation. So I'm going to bring the cos theta to the other side. So this is going to turn into sine theta over cosine of theta would be equal to sine over cos would then be 1 over 2 times mu s. But we can simplify this a bit. We have a trig identity that tells me that tan of theta is equal to sine theta over cosine theta. And now, this is crazy. Like based on like the intense free body diagram, the equation to calculate the angle reduces to something this simple. It just turns into tan of theta is equal to 1 over 2 times mu s. Okay, so it turns out all we did need is just the coefficient of static friction. So now let's plug the numbers in, or the number in. So theta would be equal to the inverse tan of 1 over 2 times the static coefficient of friction, which is 0.650. And then this is going to give me an angle that would be equal to 37.6 degrees. There are so many things I love about this problem. Like I love that we need to make use of drawing a free body diagram. We need to make use of our understanding of vector components. We need to make use of our understanding of friction. We need to make use of our equations of motion, sigma Fy equals 0, sigma Fx equals 0. We need to make use of our understanding of torque and torque equilibrium, because we actually have to use 3 equations of motion, sigma Fy, sigma Fx, sigma tau. And then everything just beautifully simplifies where you can cancel all the stuff off to get this really simple equation at the end of the day. Okay, so it's like I said, it's one of my favorite physics problems, just because you have to combine so many different things and you get such a simplified result at the very end. Okay, so in the rotational motion work booklet, you can complete, I think there's 2 or 3 problems dealing with torque. And that's pretty much it for rotational motion. In the work booklet, you're going to see some other sections on some concepts dealing with, I think, rotational inertia and rotational dynamics and rolling motion and rotational kinetic energy. I used to cover those things when I did a different AP program, an algebra-based AP program, where we actually did need to go into those in more detail. However, the AP program we're doing in Physics 30 is dealing with electricity and magnetism, so we don't really need to dive into those topics, but we need to use torque. So once we get into a certain lesson in AP Physics magnetism, we are going to have to make reference to torque. So this is kind of like the cutoff for what we need for AP Physics C, electricity and magnetism. However, I might, if I have time sometime later, just make lecture videos of the 4 remaining topics for anybody who's actually interested in a little bit more explanation of some rotational motion lessons. And if I do so, I will talk to you then.